Okay. So I noticed that in the break, I forget to write the gradient here. So please insert gradient here, okay? When I copy from up to down, so there should be a gradient here. So next thing, what I'm trying to do, study what is this equation. So I have non-homogeneous wave equations for the Lorentz conditions, and I am saying that there is one non-homogeneous wave equation for the Coulomb conditions, and let me show you indeed it is. So consider the following integral first. Following integral. One over 4 pi current density divided by x minus x prime d cube x prime. So for the newcomers, I forget to write the gradient here, so you should write again. Okay, so this wasn't in your notes. Okay. So I'm trying to calculate this and to show you that this is the longitudinal part of the current density. So to start, I said that consider the following integral, current density divided by x minus x prime integrated through the volume. And then take the curl of both sides. Curl of both sides. I am keeping this part separately here because at the end I want to show you that this is the JL. So take this, take the curl of curl. With respect to the x. Current density over x minus x prime d cube x prime. Okay? Let me tell you again. This piece I call JL should be. And under this condition, I said that this term cancel out and you can have the non-homogeneous wave equations for the transverse current density. Now I am trying to show you that this piece indicates the longitudinal current density. So I take this integral, particular integral, and I take the curl of curl. So what is the right hand side? This is a vector and this is the curl of that vector. So what I am going to obtain? What is the rule of the curl of A? Gradient of divergence and minus Laplacian. So use this. Should I multiply 1 over 4 pi, 1 over 4 pi? Maybe I can multiply later, 1 over 4 pi. I have gradient of divergence of current density divided by x minus x prime d cube x prime. This is the first term. Actually, that is gradient of divergence of this integral, but this operator depends only x, then you can take inside, okay? No problem here. Other term, minus Laplacian with respect to the x of current density, which depends on x prime divided by x minus x prime d cube x prime. Again, this Laplacian operator enters the integral because it is affecting the only x. What I have at the moment, I have gradient of x. This doesn't see the current density, and that is equal to what? Current density dot product gradient with respect to the x 1 over x minus x prime d cube x prime. Do you agree? Okay, because this x doesn't see this, and that is equal to current density dot product gradient of x minus x prime. And if you look at here, this Laplace doesn't see this because it is dependent on x prime, and this becomes Laplacian of times 1 over x minus x prime. So that is equal to, this term is equal to current density times Laplacian with respect to the x 1 over x minus x prime d cube x prime. I would give you as a homework this very little exercise, but I am doing this to remember also the some parts from the first part of the course. So you have something, you know, what is the Laplacian of 1 over x minus x prime? You know the answer. Delta function. So if I multiply everywhere with 1 over 4 pi, 1 over 4 pi, and 1 over 4 pi, this will be cancelled. And this all together becomes as what? Plus current density. This piece, right hand side, is the current density. And let us play a little bit this middle term. So that term minus plus 4 pi cancels, and that is current density. Can I looks like this integral to this one? My aim is this. Not at the moment, but say something. You can do one more thing here. Instead of this, what happens if I take the gradient instead of x with respect to the x prime, what will be? Gradient of x 1 over x minus x prime magnitude is equal to what? Gradient with respect to the x prime over 1 over x minus x prime. What is the relation? There's very simple relation. What is the relation? 1 is the negative of this. Do you remember? Yes. So that turns to be the following. Gradient of x over 4 pi current density of x prime dot gradient of x prime 1 over x minus x prime d cube x prime, and here you have the current density. Now, can you convert this integral to this one? Yes, integration by parts. So this is equal to, let us go one more step, 1 over 4 pi gradient of x, divergence with respect to the x prime of all quantity d cube x prime. And I forget to put the minus sign. This is taken with respect to x. This is taken with respect to x prime. I should put a minus sign here. And another minus. So if you write this term, divergence of all field minus, there's one more minus, that will be plus, and you will get what? 1 over 4 pi gradient of x and divergence of x prime dot current density divided by x minus x prime d cube x prime, and here is the current density. Okay? Everybody sees what I do? So for this piece, I write that the divergence of whole vector field minus, there was one minus here, minus, minus, plus, divergence of the current density and that. And if you look at this term and that term are the same, these two. And what is the first integral? This is the divergence of the whole vector field using the divergence theorem, goes to the surface integral. When the surface goes to infinity, current density divided by length goes to 0. So this will be dropped to 0 due to the divergence theorem. This will be 0 divergence theorem. And what I have here, this is plus. If I take this to the other side of this, what I am going to obtain? Current density is equal to this piece, which is exactly that piece, plus another piece. One of the pieces are longitudinal current, the other is the transverse. Why? This is the total current. And one piece is this, exactly that term. Okay? Minus, minus, plus goes to the other side, minus. And the other piece is this. Now, which one is the longitudinal, which one is the transverse? Do you think so? For J, if you say JL plus J transverse, which divergence will be the 0? Transverse. Which curve will be the non-zero? Okay? So therefore, this whole piece is equal to, should be equal to longitudinal part of the current density, and this part should be the transverse part of the current density. So the bottom line, you see some simple calculus, some tricks you use, you already know, that is the Laplacian of 1 over x prime, or the gradient of 1 over x prime is change its sign. But you show that this could be expressed as a longitudinal current, and if so, that is which was equal to this term, that was equal to 1 over c squared gradient of del phi over del t. Therefore, this is equal to mu 0 JL. JL components cancel, and you can obtain this. So you can go over these steps. So in your book, it's not explicitly done. So I did. You can look at your. This is easy. Easy derivation. Now, so the next thing, how we solve that the non-homogeneous wave equations, because we are seeing in the Lorentz conditions and the Coulomb gauge we have some non-homogeneous wave equations. So let me start and continue some point and then stop, continue on Monday. So green function for the wave equation. If you look at how many equations we have in Lorentz conditions, one non-homogeneous wave equations for wave vector potential, one for scalar. But if you write the component-wise, you can write the x component, y component, or the z component of the vector potentials. They are scalar. So basically, we will try to introduce the general solution of the non-homogeneous wave equation. We have some scalar function. So that could be scalar potential of what? Components of the vector potentials, x, y, z. 1 over c square, del square, phi over del t square. And that is non-homogeneous. You have some source distribution. That distribution depends on position and time. Practically, that could be the charge density or the current densities for each component. Now, the idea is the following. So you know this idea. Use the Fourier transform, go to the Fourier space, solve this equation, and take the inverse Fourier transform. You did many applications in mathematics, I think. Not this equation, but in different kinds. So the Fourier transform of this scalar functions could be the following: phi x omega or f x omega could be written as either of those, phi xt or fxt e to the I omega t dt. Integration minus infinity plus infinity. So if you have this one, this is the Fourier transform of the what? Psi xt. You can express in that form, or you can express this form. Okay. And the inverse Fourier transform is defined in the following form. Inverse Fourier transform, let me write for one of them. Psi xt 1 over 2 pi minus infinity plus infinity psi x omega e to the minus I omega t d omega. Take the integral through the frequency space and end up with the time, and that is valid for the other one. So let us try to take the Fourier transform of the non-homogeneous wave equation. You have Laplacian 1 over 2 pi, and instead of psi xt you can write in that form, that is equal to psi x omega minus I omega t d omega. This is the first term, minus 1 over c squared, 1 over c squared, del square over del t squared, 1 over 2 pi psi x omega e to the minus I omega t. That is the other piece, that part. That should be equal to minus 4 pi minus 4 pi times 1 over 2 pi fx omega e to the minus I omega t d omega. d omega. So from here, you can take the derivative operator del over del t square inside, take the 2 times derivative, and you can write everything in one big equation that is 1 over 2 pi in the integral form. Take the integral outside, that will be equal to, from the first one we have the Laplacian. From here, 2 times derivatives makes omega square plus omega square over c square. And we have phi x omega. And take this to the inside. 4 pi omega x fx omega, and everything is under the parenthesis of e I omega t d omega. I did nothing. So I add this operator to here, I obtain omega square, and I take the whole parenthesis of the integral, and I have one equation have to be satisfied. So this equation is the equation in the frequency domain. This argument of the integral have to be 0 in order to get the 0 result. And I know that omega over c, what is the omega over c? That is the k square, that is the wave number. And you have k square plus del square acting x omega is equal to minus 4 pi x omega. When k goes to 0, this becomes a Poisson equation. So the idea of solving this, how was the idea for solving this equation? You studied the case of k equal to 0, that was Poisson equation. You put a source as a delta function and you try to find the solution. And you say that the dead solution should be the Green's function if you put the right hand side as a delta function. So we will do the same thing here. So Laplacian plus k square. As a source, I will put a delta function x minus x prime, and I'll call this as a Green's function for x prime. So substitute to the right hand side delta function, say that the solution will be the Green's function. So suppose that I know the Green's function. Suppose that I find the Green's function. How do I find the full solution of psi? Do you see from here? This is very simple. Multiply both sides fx omega, integrate through the volume. Delta function of fx omega, x prime omega, say x prime omega, sorry. Multiply both sides fx prime omega to both sides. Integrate through the volume. Due to the delta function, this will be minus 4 pi fx. And here you will have an integral. Green's function times the what? The source. Source and integral. Source and the Green's function convolved, and it's the integral, and that is the solution. So why do people put a delta function and define the Green's function? Because they can solve every kind of source. For every kind of source, they solve this equation once they know that the Green's function. So this is the idea. So I'll call R as a x minus x prime, and the x minus x prime magnitude is the R magnitude. The equation turns to be the following. For the right hand side, that be minus 4 pi delta R. And for the left hand side, for that term we have k square Green's function, and you need a Laplace operator. So the Laplace operator for the radial part, you can write 1 over R d square over dr square rg. So I can find the solution of this easily. When R is not equal to 0, delta function is 0. That is very easy equation. This becomes to what? If R not equal to 0, d square over dr square rg becomes k square rg. And what is the solution of this? What is the solution of this? Is k is positive? Yes, it's positive. And then the solution is what? Sines, cosines, or the exponentials. So basically the Rg, the solution form this is a mixture of e to the ikr plus e to the minus ikr. And g could be plus or minus ikr over r. Plus and minus will have a different meaning. We will see later. Now, this term is 0 when r is not equal to 0. The other case, what is the other case? When r close to 0, what will happen when r goes to 0? So write the equation again, d square over dr square rg k square rg minus 4 pi r So what I do, multiply by r to the both sides. So that will be what? Minus 4 pi r delta r. So when r goes to 0, which term goes to 0 first? Which term goes to 0 first? If you put r equal to 0, okay, everything could be 0. But if r goes to 0, you have one choice. What is the k? K is what? Wave number. Some wave number, some length, 1 over length square. So r times k square goes to 0 more rapidly than the other terms. So basically, you can ignore this term. So when r goes to 0. Then, if if you integrate this, so you end up, this term will be ignored. So if you integrate this, what you are going to obtain? You will obtain what? If you integrate left hand side and right hand side, your integral cover the r, that will be the 0, and then one integral of this d over dr rg will be constant. Okay, if you integrate the left hand side and the right hand side. Okay. So our, it doesn't matter. Basically, it's okay, but you will cross that the r equal to 0. You are right. So basically, G could be, so that means that, sorry, I am sorry that this is not, this is 0. If I integrate this both sides, r times delta function will be 0. I'm sorry that, okay, that will be 0. And one integral of this will be the d over dr, and that means that rg is constant. So let us freeze the constant as 1, and that will be the g will be 1 over r when, let us say, kr goes to 0. So both solutions are consistent when kr goes to 0, because when kr goes to 0, this drops to 1. This is 1 over r, and consistent with this one. Okay? So I'll take the full solution in that form, because it is satisfying that when delta function is not equal to 0, or when the delta function is equal to 0. So the presentation will be the following. G, we have the plus or minus case. Both depends on k, wave number, and r. And that is e to the plus minus ikr over r. And that is equal to e to the plus minus ik x minus x prime over x minus x prime. Okay. Now let us remember that the time-dependent form of the wave equation again. So for the source, instead of x minus x prime, write delta x minus x prime, delta t minus t prime. So this is the source in terms of delta functions. And for the left-hand side, we have del square x minus 1 over c square, del square over del t square. And we have that function, some Green's function, has the plus minus solution x t x prime t prime. So this is a wave equation. Now here in the source includes the time also. What happens if I take the Fourier transform of the right-hand side? What happens if I take the Fourier transform of the right-hand side? So tell me the Fourier transform of the right-hand side. You will multiply e to the I omega t and integrate. And what you are going to obtain? If you multiply this e to the I omega t and integrate through the t, instead of t, you will put t prime. So your right-hand side, if you take the Fourier transform, will be 4 pi delta x minus x prime e to the I omega t prime. If you take the Fourier transform of the left-hand side, we already did. What is the result? That is equal to Laplacian plus k square times what? This. So let me say plus of r for k. But is it sufficient? So if you look at the left hand and right hand side, there is something wrong. So this has a e to the I omega t prime, and this doesn't. Therefore, your solution should include this one also for the time-dependent part. So g x omega could be written as e to the plus minus ikr over r e to the I omega t prime. We studied the form of this form, and we find the solution of the Green's function in the Fourier domain in that form. But if we have a time-dependent form, the Fourier transform brings us to the e to the I omega t prime. Therefore, there should be I omega t prime here. These terms will be cancelled, and you can get the original one. So this one is cancelled out, and you can obtain the previous one. So the next step, take the inverse Fourier transform of this and find the Green's function. So this is very simple. The rest is simple. The Green's function xt x prime t prime will be 1 over 2 pi Fourier transform of the Green's function e to the plus minus ikr over r e to the I omega t and times e to the my I omega t d omega. So this is nothing but, this term is nothing but gx omega. So that is the Green's function in the frequency domain. We are converting to this to the time domain, taking the Fourier transform. And if you take this from minus infinity to plus infinity, you will obtain 1 over 2 pi minus infinity to plus infinity e to the I plus minus ikr over r e to the minus I omega t minus t prime d omega. So any question here? So let me call t minus t prime as a tau. And what is k? K is equal to omega over c for non-dispersive medium. And the Green's function r tau, r is x minus x prime, tau is t minus t prime. Plus minus has different implications I will discuss in a moment. Our integral becomes 1 over 2 pi e to the I plus minus omega over CR over R e to the I omega tau d omega. So let me go one more step. 1 over R 2 pi, and if you combine the terms you will obtain e to the I omega tau plus minus R over C d omega. So take this 1 over R outside and you end up this one, and you know that this integral, what is this integral? You know this integral, minus infinity plus infinity. This is the delta function, definition of the delta function. So that term is equal to tau plus minus R over C, and altogether the Green's function could be written as plus minus R tau 1 over R delta function tau plus minus R over C. So I will put the t minus t prime and r minus x prime and try to interpret what is this. So do you have any question here? So basically it is simple. We have the wave equation, and the source is the space and time. Take the Fourier transform, it introduces e to the I omega t. Therefore, your solution should introduce some I omega t prime. You know that the time independent form, and take this and take the inverse, take the Fourier transform and inverse Fourier transform, and find that the Green's function in that form, and if you put the values, you will obtain the following. So the Green's function will have delta. If you say instead of t tau t minus t prime, you will obtain delta t prime minus t plus minus, instead of r, you can write x minus x prime over c divided by x minus x prime. What does it mean? What does it mean? So you have an event and you are observing later. And what is the time interval between the event to observing point? X minus x prime over c. So plus, what is the meaning of the plus? So basically, if you substitute here t minus t prime and here x minus x prime, you will obtain this. And one of them is corresponding to the advanced Green's function, and the other is corresponding to retarded Green's function. Which one is corresponding to retarded? Retarded means that the event occurs and we see the event later. How do we get this information? We get this information here. When we have t and t prime, we have the delay. It's a t minus t prime. What at which speed it will disperse? K. What is the K? K is omega over c. That means that in free medium it goes in the speed of light. So basically, one of them is corresponding to the advanced Green's function, and the other is corresponding to the retarded Green's function. So it is a matter of definition. So the event occurs at t prime, and you can observe the event at some time t, and that separation is the delay time is nothing but x minus x prime over c. And using this Green's function, you can solve every kind of the non-homogeneous wave equation. Is the signs are okay? So next time, so we will see this when we study the scattering, and also in somewhere multiple expansion we will have non-homogeneous wave equations. And the other thing, in next time I will study that the conservation laws, conservation of energy and momentum, and continuity equations, and then I'll discuss the chapter 7, that is the plane waves, refraction and reflection of the plane waves. Okay, so do you have any question? I would advise you go over these things by yourself.